in this last part of Unit 3, we'll talk about this design principle for algorithms, divide and conquer, a little bit more outside of the narrow context of sorting where we've seen it. Again, some really basic fundamental questions that we will tackle. It will be just a brief glimpse at it, but I think these are worth knowing, and it's helpful to keep in mind if you design algorithms. There are certain principles that work across different algorithms, and divide and conquer is one. You may have, if you had an undergraduate algorithms class, you may have seen others. There's greedy algorithms. There's branch and bound for optimization problems, and dynamic programming is another big one. We'll only really talk about divide and conquer here because that fits well into the topics we discuss anyways. If you want to learn a bit more about this and you're eligible for this, there's a follow-up module on advanced algorithmic techniques in the second semester. For here, we'll keep it with divide and conquer. And you've actually seen this before. I pointed this out for both quicksort and merge sort. So let's see where this comes from. The name just comes from this Latin phrase that at least Julius Caesar was using and many other people used. One definition from a dictionary for divide and conquer is to make a group of people disagree and fight each other so that they will not join against you. I guess you see this in politics in many ways. It's not exactly the nicest way to proceed. It seems effective though, sadly, or as a matter of fact. For algorithms, it's much less controversial. And I think often it's just a little a cheeky piece of terminology. You'd find this in algorithms often, that people think it's funny to call things that provoke associations to other fields. Sometimes it's helpful just to build a metaphor, and sometimes it's just a little silly. I'll leave it to you if you which category this one is. For the computer science perspective, question?
So I'm struggling to see how binary search is divided. Is binary search a very linear way? It doesn't feel
Yes.
You're not like solving. You're not like solving the other branches. Like when you're doing the binary search algorithm, once you exclude an entire house. You don't like
Yeah, I agree. So the comment was that binary search might not be the cleanest example. I'll come back to this. I agree and disagree in a way. It's okay. It's a soft definition, right? This is not a mathematical definition. It's a vague thing, and so we can live with both agreeing and disagreeing in a sense. What I would say in computer science, what is divide and conquer for us for algorithms, is some method that breaks things into smaller parts, and you can recursively solve those. Usually, we think of these recursive parts of non-overlapping in some sense. And there must be a way to assemble the solution for the entire problem from the solution of the subproblems. I think undeniable examples are merge sort and quicksort, where you do exactly that. Merge sort is the most classic one, the poster child of divide and conquer. You cut exactly in half. You have two equal problems. You recursively solve those, and then there's a bit of a step afterwards, merging them to get the solution for the entire problem. Quicksort is slightly different. You spend a little more time before you recurse, and after the recursion, actually nothing needs to be done. Binary search, in a way, is not the cleanest divide and conquer because you only really solve one of the subproblems. In a way, I would still say it can be classed as this. You break the problem into two parts, and then you discover that you only need to solve one of them. As I said, was maybe similar for Towers of Hanoi. You kind of use a solution for subproblems twice. It's still, in a way, breaking the problem into smaller pieces. I think the exact boundaries of this are super vague, so don't get too obsessed with the term. It's more if you have to solve a new algorithmic problem, take it as inspiration. Maybe something divide and conquer works. And if it does, great, then you solve the problem. And if what comes out is not the nicest, cleanest example of divide and conquer, who cares? You solve the problem. I just want to show you a few other examples. And actually, one of them will be of the binary search type. So you might disagree again that this is maybe not divide and conquer in the cleanest form. The first part I want to show you is order statistics. So it's another classical comparison-based problem. And let me motivate this a little bit before I show you what the concrete problem is. If you do some data science task, you have numerical data, a lot of it, and you would like to see a quick summary. What does this data look like? A standard thing, and it's so standard that Pandas, this Python library for data science, has actually a simple call for this. I think it's called describe on a data sequence or data frame column. So it's this is something that people do a lot. If you have a lot of numerical data and you'd like to have a concise summary of what is it like, a standard thing is to do all of these and look at those together. You want to compute the mean, so the average value, and the standard deviation to have some feeling of where is the data on average, I guess, and how much does it deviate from that. You may also want the minimum and maximum to have some more tight bounds on the range. So what's the outliers, if you like? Where are they? You can have a little closer look with a histogram. If you know the range, you can break the range up into, say, 10 pieces and look how many of the data points lie in each of these 10 pieces. Then you get a histogram. And then the last bit that people often like as well is quantiles, or as the special cases, the median, which is the value so that half of the data is smaller and half of the data is bigger. And quartiles is the same with, it's a point where a quarter of the data is smaller and 3/4 is bigger, or the symmetric version, the third quartile where you have 3/4 smaller, 1/4 bigger. That just gives you another angle of seeing where the range is for the majority of the data. As that's what the describe function usually shows you in Pandas, and what often helps you to just see a rough picture of the entire data. You may have seen these box plots, box whisker charts. They are all variations of that. So the question is, how can we compute this? If you wanted to implement such a function, the describe function, you start thinking about how to compute all these. And it turns out for the first three, it's quite easy to do in a linear scan over the data. In one way or another, okay, maybe for standard deviation, you have to think a little bit, but there's formulas to do it. Even in online mode, you can add 1 point at a time, and you can keep a current, a running standard deviation. It's trivial for the mean almost, but you can do it for standard deviation as well. And for the others, it's also easy. But there's the fourth one, where it's maybe not so clear if you can do it in linear time.
Which fourth?
This fourth, computing quantiles. Now, okay, let me first formally define what the problem is in the general case. I call this finding order statistics. So these guys are called order statistics because they're statistics from the data, summary points of the data that depend on the order only. And the algorithmic problem, I called it selection by rank. Sometimes it's also just called selection, but it's a bit unspecific. What you really have is you want the so-and-so smallest data item. That's why what we called rank before. So you give it an array of numbers and a number k, an index in that array if you like. And the goal is to find the value that goes into this position if the whole array was sorted. Now, we could obviously solve this problem by just sorting the entire array. And we've seen many methods to do that. and maybe the array is partially sorted, right? Then you could even take advantage of that, as I've shown you last week. But there's also a way to avoid sorting altogether, at least most of it. Some special cases for k is the things we mentioned before. It actually generalizes min and max as well, which is nifty. Which also shows you for minimum and maximum, the problem is very easy. A linear scan is enough. You just keep the current minimum. Whereas for the general k version, if you want the median, it seems less clear how to do this without sorting. All right? Question?
I'll think about sorting. So like for median, you could split the array into the try and find. Okay, so split the array into all sorts.
I should have put a Slido question here on how many people have seen this already. I guess quite a few will have. As always in this class, I guess it's roughly two-thirds who have seen it, and a third is puzzled. So same problem as always. But let me show you a solution. And the solution goes by the name of quickselect. Anyone remembers quickselect? The quick Slido free version. Who remembers quickselect? Quick hands. Who has never heard quickselect? And the remaining 90% are unsure. So it's a classical algorithm, and you'll like it once you've remembered it. The key observation is if we have an element, it's relatively easy to find its rank. You could just take the element, compare it to all the others, and count how many were smaller. That's the rank. If you have a rank and want to find the element that has this rank, that's a little less clear how to do it. But you can take this easy task and move your way through until you found something. Well, okay, that explanation wasn't too great. What you do is you pick an arbitrary element and you find its rank. Suppose that rank is j. What you wanted was the rank k. There's really just three possible cases now. If you found exactly by chance, you picked an element and it was the one you were looking for, lucky you, and you're done. Not usually the case. So if the element you found is smaller, its rank is smaller than k, you still learn something, because all the elements that are even smaller than this element are definitely not the element of rank k. This one was already too small. The others are even smaller, so throw them away. And similarly, if the element you found is larger in rank than the element you're looking for, all the elements that are even larger are not needed anymore. So far, so good? Now, how can we make use of that? This is really something we've solved already. Taking an element and finding its rank, we called this partitioning in quicksort, but it's actually the same thing. Quicksort picked a pivot and found for every element is it smaller or larger, and it returned the rank. It returned the position of the pivot. Now, the partition function has the nice side effect that it doesn't just find the rank, it also changes the array so that everything smaller is on the left, everything bigger is on the right. And that's convenient because to do this elimination step, we don't just want to know that we can eliminate some elements, we want to know which ones, right? So what we do in terms of code is exactly that spelled out. We choose our pivot as before, and there's an asterisk to as before that we'll come back to. But suppose for now we just pick some random element as our pivot. We do the partitioning step, and that comes back with the rank of the chosen element. We have no control over j, really, but we can distinguish the cases. We could be lucky, then we return it. Or we could have an element that's too small in rank. Remember, too small means everything that's even smaller can be thrown away. So we can recurse on just the elements that are larger, which is the right part of the array. And so the only bit here, the tricky bit, is you have to adjust the rank you're looking for. If you were looking for the kth in the entire array, if you now throw away some small elements, you have to just subtract the number of elements you threw away. And that's what's happening here. I guess it would have been nicer to write k minus j plus 1 in parentheses. Of course, the same thing. And the other case, if the element you found is too big, then you throw away all the even bigger ones. So you recurse on the left part, and in this case, the rank stays. Okay? And that's quick select. Notice that it's quite similar to quick sort, hence the name, but it only recurses on one side. You never need to go on both sides because you're only looking for a single element which can either be to the left or to the right of the pivot. Okay? Because of that, because you only have a single recursive call, you can rewrite the code to just avoid the recursion and make one big loop out of it. If you've seen similar things, that's not too surprising. That's usually the way you want to implement it because it's more efficient. But just for presenting the code, I think this is easier. All right. How good is quick select in the form I've shown to you now? Unfortunately, the worst case is really poor, and the reason is just the same as in quicksort. You could get repeatedly unlucky by always picking as pivot the element that's largest. Suppose for the sake of the argument, you're looking for the minimum in the array, and you call quick select for that, which is not what you should do, but suppose, well, if you implement a library functions, users will call it even with nonsensical arguments, get used to it. So suppose you try to find the minimum and you always get the maximum as the pivot, then you always exclude just a single element and you spend linear time in partitioning each time, so you get this quadratic worst case again. It's the same argument as in quicksort, and that's terrible. However, you can prove that this is kind of an isolated unlucky case. Most of the time, in a similar sense as for quicksort, on average and more, you only need linear time. And linear time is probably the best you can hope for, because even if I gave the element to you, just to check that this actually has rank k would take you linear time. So there's no way to get it faster. What's nice is we don't need any extra space, not even the recursion stack if you get rid of the recursion. You can tweak this same idea to find more than a single order statistic in one go. The reason I'm listing this here is if you do a box plot, you want to find the median and the lower and upper quartile. You could call quick select 3 times, and that's fine. You can also modify the code to find those 3 in one go, which is a slight bit faster. So if you do this many times, it might be worthwhile doing. So I listed it as a positive because quick select makes this fairly easy. It's not relevant for the module to know exactly the details. So I've used these two personas a lot in the next chapter. So here they already come up. There's the programmer, who is the practitioner's point of view, which really says, I'm using quicksort to sort all the time. I might as well just use quick select for finding order statistics. It's probably more likely that some sunstorm flips bits in your memory than that you see this quadratic worst case. Whereas this guy is the theoretician who is interested in the internal truths and the worst case things and so on. And he's worried about this worst case. And so it's as an academic question for sure, and maybe for security reasons sometimes as well in practice, it might be worth knowing if you can do it in worst case linear time. This gave us only expected linear time. Okay? We can do worst case n log n by sorting. That's at least close, but that's a bit lame, I guess. theoretician won't be happy. Pardon?
If you're going to compute multiple order statistics, it makes sense to sort before compute them.
Okay, if you need multiple order statistics, I think the question is how many. If it's a constant number, say 3, 3 times linear is still linear. It's still better to do that as opposed to sorting. If you need a lot of them, I guess log n, right? Then there's a point for sorting. If you're smart, if you this is really tough to quantify. However, if you run quickselect, it will make the array slightly sorted because it partitions at some points and it leaves that as such. So you can, if you remember the pivot points that you already had, then you can try to speed up future calls to quickselect so that you never do more than this full sorting work, but you can do just as much as you need it organically. That's a side remark. Like, again, is a nifty thing you can do. Well, it won't be on the exam if that's what you want to hear. Okay, questions on quickselect? Now coming back to this question, can you do it in worst case linear time? The answer is yes, we can do it. What we need is better pivots to avoid this worst case. So far, so obvious. For example, if the pivot we got was the exact median all the time, we'd be fine because we would cut the remaining number of elements in half in each step, at least. Maybe we're even lucky and get the element we're looking for earlier. But we definitely get away we get rid of half the elements each time. And that's, okay, I wanted to show this picture first. Suppose we could get rid of a constant fraction each time. And this picture is for getting rid of half of the elements each time. It's a visual proof for the fact that the geometric series converges to a constant. But if you're more visually inclined, 1 times n, that's the starting state. You have all the elements. You cut it down to 1/2 in the first step. Then you cut it down to 1/4, to 1/8, and so on. That's why you follow this spiral in. And you see you always have enough space to fit the next 1/2 in the remaining little bits. So the overall box that you need is just 2 times the starting point. I think this picture is more valuable than quantifying this more precisely. Whenever you design algorithms, if you can somehow make it so that the recursive call is on just 0.9 the number of elements that you had before, and you don't spend more than linear time for each step, your overall cost will be linear. And this is the visual proof for that. If you don't have a factor 1/2, you get a different constant than 2. Yeah. Yeah, if you write this down, it would be some geometric series of this type. You would normally stop at some n, but you might as well extend it to infinity. And in this case, that's 2. And if you have some other factor here, if I put this, alpha here, the general is 1/1 minus alpha. So you can work that out. In the picture, alpha is 1/2. So that's kind of the visual proof. If we had, in each case, the median as our pivot, we'd be fine. But of course, that's not too helpful if we're trying to design an algorithm to find the median in the first place. We already need our own solution. And in this case, recursion doesn't save us because it would be recursing on the very same problem. I want to find the median of these n elements. Oh, I can do quick select. I'll just find the median of these n elements quickly, and then, oh, hold on. Right? So it doesn't help us. You would recurse on the very same problem. But if we could do something like this, that'd be good. And this remark says it doesn't have to be the exact median, as long as you can guarantee it's in graphical speak. So as long as you can guarantee that the pivot is in here, and this part is epsilon times n for a fixed constant epsilon, then that's enough for this kind of argument to go through. So can we somehow do this? Can we find not the exact median cheaply, but somehow something not too far away from it? And it turns out we can. It's a little more convoluted. So the idea is we split the elements up into groups of 5. And from these 5 elements, we just sort those, and we take the middle one. Pardon? Why 5? 5 is the smallest constant so that this works. You can do a slightly larger one. That's the smallest where it goes through. Or you can make it, you can do it with 17 if you prefer. So from all the elements, you just keep the middle one out of 5, and on that you recurse. So let me go a little slower. This code basically does this. Split the elements into groups of 5. So there's a loop. M will be the number of 5er groups, and there might be one left over where we don't have 5 elements, right? For each of these groups of 5, we sort these 5 elements. So that's just a tiny section of the array. We sort this with whatever method. I don't care too much at this point. It's only affecting the constant factor at the end, so you can be smart about this. And then we take the middle one. So 5i plus 2, that's this black guy. And we swap it to the beginning of the array. That's just to keep all these middle ones together. So I'll take these and put them at the beginning of the array. And all the others are behind that. OK? And then I'm calling the quick select algorithm recursively on this bit and find the median. Now that is, again, something like we're using ourselves, but this time on a smaller problem, and that's why it's going to work at the end. It's a problem that has, at most, every 5th element. OK? Amazingly, the rest of the algorithm is unchanged. Instead of picking some random pivot, we call this function, which chooses the median of this prefix. And then the rest is as in quick select. We use that as in pivot, we partition, and we do what we've done before. The amazing bit is that this is good enough and that it's linear time. Let me point out that this is a mutually recursive function now. We have 2 functions, and they both call each other. This one calls choose pivot, and this one calls that one again. So it's not visible from just looking at the lower function, but we actually have 2 recursive calls. The first one from choosing the pivot, and then later from the main recursion. OK? So the first recursive call has at most n over 5 elements. That's just by choice. So that's the easy one to analyze. For the second recursive call, we'll have to work a little harder to see on how many elements it can, in the worst case, work. Here's the picture I started drawing slightly more nicely. So these are our groups of 5. and there might be one group left over. From all the groups of 5 that are complete, we take this middle element, and from all those middle elements, we select the median. That's why the algorithm is called median of medians algorithm. So here's our median, and notice that if you have an even number of elements, you have to break ties. There's actually 2 elements that could count as a median. I'm choosing the smaller one arbitrarily. That's why it's rounding down here. So this M, that's the pivot element. That's the one that determines how we partition and how we recurse. Now, how many elements can, in the worst case, be in this recursive call, in either of these recursive calls? And for that, you have to look at these shaded areas. We know that all the elements above the median in the 5 are smaller than the black one, the middle one, because they're sorted. So in each column, the 2 topmosts are smaller than the middle one. We also know that these are all smaller than this median because that's the median. So if we arrange them in sorted order of these middle elements, then okay, zooming too fast is dangerous, but it worked. So this is smaller than the median, this is smaller than the median, this is smaller than the median, which means transitively, these are all smaller than the median, and these, and these, and these 2 anyways, because it's in its column. Okay? So we can, in each recursive call, we either get rid of this blob of elements or of this blob. And the smaller is this top, this is left upper one. So how many elements are in there, roughly? It's half of each, it's half of the columns, because it's the median. And in each column, we get rid of 3 elements. So it works out to 3/10 as a fraction of all elements. And if you use this in a recursion for the cost, so you can write C of n as the overall cost for the algorithm, again in some abstract cost measure. You have a linear term for the partitioning. That's this call. And you have the 2 recursive calls. You're using the worst case size. Question?
Yeah, if you choose a larger number than 5 for the number of errors in column, if
Yeah.
it gets closer to n over 2 or
So if we use a larger number, if we make the columns taller, more than 5 elements, I don't think that this part improves much. So the red blob actually gets smaller, but the recursive call up here gets smaller because you're just recursing on every 17th element instead of every 5th. But you have to balance it out with the sorting cost for each column, which grows. So as long as you keep the columns of constant size, it only affects the overall constant. And there's some trade-off. The original paper where the researchers proposed this algorithm, they tried to optimize for this size of the column. I think it was something around a dozen elements worked out best, but that depends on the assumption of the cost. There's different types of costs you have to trade against each other. If you stay with the 5 elements, then you're left with this recurrence. And a simple way to argue why this is linear is to just start with the assumption that the cost is linear and then prove that this is a correct solution. The details are a bit more messy, and so I left those out. But you can formally prove that this recurrence is upper bounded by some recurrence like this. So you have linear cost for the partitioning, and you have recursion on total size 90% of what you had. And remember from the last slide, that's good enough to guarantee overall linear time. As long as you can have a constant strictly less than 1, you get linear time. And so that's worst case. So even theoreticians happy now. I can mention that there's an intermediate version between those two extremes, picking some arbitrary pivot and picking this really, really good one where you can guarantee that it excludes a fixed fraction of the elements, where you take a larger sample of the elements and pick the median from there, but you use a much smaller set than every fifth element. You can pick something like square root elements from the randomly chosen from the array and find the median from there. Then theoretically speaking, in the worst case, you're still quadratic or close to it, but you're even less likely to ever see a bad runtime, and you can improve the expected case further. Pardon?
Why would it still be quadratic if you're choosing a pivot from the median of the square root of the?
You can still, so the question is why is it still quadratic if you use such a large sample? I guess you can still have the largest element in the sample. So say the sample is the square root n largest elements, so you would just exclude square root n elements, but you're left with n minus square root n, which is by and large not much better than n. Yeah. Okay, so much for this. That's still an application of divide and conquer, but a little more sophisticated in the way they interact. It's no longer just splitting in half.